Our next unit is work and energy. I'll be posting the homework on this afternoon, maybe tomorrow morning. I have a few more I want to write. It's like the last one. I am trying to ensure that I have, either way, we are on Unit 3, and Unit 3 is work and energy. Our next two units are specifically ways to deal with force that allow us to kind of skirt the idea of having to use Newton's laws. As I said to you before, the force concept model is a method that can be used to solve problems, but it is a complicated method. There are other ways of using Newton's laws in order to find things out about the way a system will behave. Work and energy is one such way, but it's not just a construct. Work and energy is a means to deal with force and the implications of what happens when an object experiences an unbalanced force. So we're going to break this up into kind of two parts, and we'll start with the technical definition of what is work, because there are two, what I would say are probably more seminal measurements in physics than force. Force is an interesting concept, and I like it, but work and energy and impulse and momentum use force to demonstrate what can be done with physics in a more meaningful and robust way. So we'll start with work. By definition, work is the means by which a force can be used to change an object's energy. It's a whole big sentence, and you should write it down. I mean, I don't really care if you know it. I will never ask it on the test, but I think it's important that you know. Work is the means by which a force can be used to change an object's energy. Kind of funny that we have this definition, because if I ask you this next word and ask you for its definition, I'm concerned about what I will get. But I've asked these kinds of questions in the past, and it's always kind of fun. Can somebody tell me a definition for energy? Objects have energy, and objects interact with other objects through force. Force is the means by which one object can give its energy to another object. I'm going to say that again, but that's how this works. This is the whole construction. The nature of the force concept model is about how you give an object energy. Force is the connection. It's the means by which one object can give energy to another object. So the moment two objects are interacting through a force, energy is being exchanged in that process. This is why Newton's third law is so critical. For every force, there's an equal and opposite reactive force, which means for every object that is giving another object energy, that object is losing energy. There is an absolute finite amount of energy in the universe. It just simply transforms from one material to another material, from one form to another form. But the net energy of the universe stays the same. Now, it's interesting enough for a conversation like that, but it's at least some place to start. We're going to talk about technical definitions of work for the next few minutes, but I want to remind you that we are not leaving Newton's laws. We are focusing on how a force can be used on a single object. That's what work will be about. But every time work is being done on an object, there is work being done on something else because of Newton's third law. Everybody follow along with that statement? We tend to talk about the agent and the object. If the agent is doing work on the object will also be doing work on the agent. So the agent-object model will be discussed in here when we talk about work. Technically, here's the definition of work, and I will write out the word work for quite a while, because otherwise I write just a capital W, and I don't want you to be confused with weight. But the technical definition of work is an integral. So that might cause some of you to be disturbed. But I'm going to give you several definitions of it. This is the technical definition that you are supposed to know. But because that definition is got some math in it that might be beyond some of you, I'm going to give you a another way of writing it. The second way is for any time in which the force is a constant. The first way allows for more flexibility for any force. So the top one covers any range of forces, even if that force isn't constant, but the bottom one covers all situations in which the force is constant. This dot in the middle is not multiplication in the sense that you're familiar with. Force is a vector quantity, and displacement is a vector quantity. But work is a scalar quantity. Energy and work is a scalar, meaning it has no direction, which is one reason why we want to get into energy, because it has no direction. We don't have to worry about vectors when we start dealing with energy. So objects either have energy or don't have energy. So we don't have to worry so much about the direction, but in order to do that, you have to understand that the thing that is giving or changing the object's energy has direction, and it's based on how that force causes the object's position to change. This is what work is really about. Whenever a force is used to displace an object, work is being done. I want to say that very clearly. Whenever a force is used to displace an object, work is being done. So you can push on the wall all you want, but if the wall doesn't move, you're not doing any work. Work can only be done if an object's position changes. That's what this relationship's about. The problem is this multiplication we have in the middle. This isn't standard multiplication, it's a vector multiplication. There's two different ways to multiply vectors together. There's something called the scalar product and the vector product. This symbol is for the scalar product. It's a way of multiplying two vectors together to get a scalar. And the way the scalar product works is we take the force and we say the product of the force and the displacement for a scalar product is how much of the force is in the direction of the displacement. You see, in order for a force to do work, it has to be in the direction of the displacement. It's the only way a force can do work. So you can have lots of forces acting on an object, but only the parts of those forces that are in the direction of the displacement are doing any work. It's pretty easy to write. It's just force times displacement times the cosine of the angle between them. That's how you do a vector product, a scalar product. The cosine always has given you the amount of one vector in the same direction as the other. That's what it's always provided. The sine has always provided how much of a vector is perpendicular to the other vector. That's why sine is the opposite side and cosine is the adjacent side. So this has always been the part of the force that's in the direction of the displacement. That's why we use cosine. And this is how you calculate work. Now, just simple stuff that you need to know. Force is measured in newtons. Displacement is measured in meters. Together, Newton meter is called a joule. So the unit of work, the standard unit of work, and the standard unit of energy in this class is going to be the joule. Let's just look at that. Kilogram meter per second squared times meters is kilograms meter squared per second squared. That's a joule. I don't know this, you can see joule here, but you can certainly see work there, Newton meter. Point of reference. There's something we're going to study later called a meter Newton. And it's in this order on purpose to differentiate it from Newton meter. This is a separate unit. We would not call this a joule. This is something that's referred to when we start talking about twisting and turning things, and this is how you calculate something called torque. So understand that Newton meter is specific, is kind of specific. We're saying we're talking about joules there, while meter Newton is about applying a torque, trying to twist or turn an object. just little things I think you should know. For every 1 joule, for every 4.19 joules, that's 1 little c calorie. So if you're looking for the thermal equivalent of a joule, that also tells you that a joule is the smallest unit of energy that you probably have encountered. There are smaller units of energy, but they tend to be used for atomic and nuclear measurements. Electron volts are very small units of energy. But for us, the joule represents the smallest unit of energy. You're also familiar with the kilocalorie, I think. Is that true? So you are aware of the difference between the big C calorie and the little c calorie. So 4,190 joules is equivalent to the food calorie equivalent. So if you ate a 200 calorie candy bar, you would have to push on a box for a long ways to get rid of all of those calories, right? You can see the mechanical equivalent. How do you think those treadmills and those workout machines in the gym tell you how many calories you're burning? They're doing this math. The force applied, the distance you've applied it for, and just doing it over and over again, telling you how many calories you've burned. So these are all equivalent types of measure, but we tend to reserve these for thermal calculations and these for mechanical calculations.